In this chapter, we're going to be discussing discrete probability distributions. Let's recall what the word discrete means back from chapter 1. A discrete variable is a countable number, not a continuous number, which means you can have a range of possible variables between all the integers. In Chapter 5, we talked about the idea of probability, specifically the idea that more times we conduct an experiment, the more accurate the empirical probability will be. This is, of course, using the law of large numbers. The empirical probability becomes more and more closely related to the theoretical probability or the classical probability when the n, or the number in your sample, increases. We also learned how to verify that a given scenario is a probability model. In Chapter 6, we're going to introduce probability models for random variables. Random variables are numerical measures of the outcome to a probability experiment. We will discuss the distribution of the discrete random variables, and then we will discuss a specific discrete probability distribution, which is called the binomial probability distribution. Continuous variables will be discussed in Chapter 7. First, let's discuss discrete random variables. As you recall, back in Chapter 5, we were interested in a particular outcome, like getting a heads on a coin toss. Instead of being interested in a particular outcome, we might be interested in the number of heads that appear when flipping a coin 2 times. A random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Random variables are typically denoted using capital letters such as uppercase X. A discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with spaces in between each points. This is what makes them countable. They don't necessarily need to be integers, but they need to be countable values. A continuous random variable has infinitely many values, and the values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So let's look at the examples down here and determine which of these variables are going to be discrete and/or continuous. The number of light bulbs out of 20 that burn out in the next week. This is going to be a discrete variable. And the reason it is a discrete variable is because you can have 0 light bulbs burnt out, 1 light bulb, 2 light bulbs, 3, 4, 5, all the way up to 20. So x can be any integer from 0 up to 20. X represents the number of light bulbs that might have been burnt out of 20. And you could have any of these values. Clearly, you cannot have 1.5 light bulbs that are burnt out. How about the time that it takes to fly from New York City to LA? This is a continuous variable because you could have any interval of time in between a certain number of hours. X can be any number as long as it's greater than 0, because it does take some time to fly between those two cities. And I can have any countable number in between that time. So if I were to be looking at a number line, 1 hour, 2 hours, and so on, the time that it takes to fly between New York City to LA can be any time in between any of those variables. They're not specific points. They're not specific points on a graph. It's an interval in between all of those points. It could take 1.5 hours to get there. It could take 3.5 hours. It could take 3.465 hours, and so on. Time is always going to be a continuous variable. Whereas this one up here, where it was discrete, we have only the values of 0, 1, 2, all the way up to 30. So you can only have specific points with space in between those points on the graph. How about the number of hits to a website in a day? Well, let's look at a number line. The number of hits to a website, well, you could have 0, you can have 1 hit to a website, you can have 2 hits to a website, and so on. But can you have space in between here? Can you have a half of a hit to a website or 1.5 hits to a website? And the answer is no. This is again going to be a discrete variable because they are countable values where x can be any number between 0 up to essentially infinity. How about the amount of rainfall in Seattle during the month of April? Again, looking at a number line, we could have 0 inches of rainfall, we could have 1 inch of rainfall, 2 inches of rainfall, and so on up to infinity. But can you have half an inch of rainfall, 3/4 inch of rainfall, 2/3 inches of rainfall? And the answer is yes. This would be considered an interval of a continuous random variable because you can shade in all of the intervals in between the countable values. So we would say this is a continuous random variable where x can be any number greater than or equal to 0. Then we have what is called the probability distribution of a discrete random variable x. It provides the possibility of values of the random variable and their corresponding probabilities. A random distribution, probability distribution, can be in the form of a table, a graph, or other mathematical formula. These are 2 rules that we already know. We already learned these back in the probability chapter. The probability of an event x that might occur will always fall with these 2 characteristics. The sum of all of the individual probabilities will always add up to 1. An individual probability will always be a number between 0 and 1 inclusive. In a probability histogram, the horizontal axis will respond to the value of the random variable itself, this will be x, and the vertical axis will represent the probability of each occurring. Clearly, the taller the bar, the more likelihood that that particular x is going to occur. In order to compute the mean of a discrete random variable, you must multiply the value of the random variable by its probability and add these products. This is also what is called as a weighted average. An example of a weighted average would be how GPAs are calculated. Your GPA is being calculated by taking the number of credits of each course into account. In other words, if you were taking a student success course for 1 credit, and you were also taking a biology class with a lab worth 4 credits, we would weight the grade in biology 4 times as high as we would your student success course because you would spend 4 times as much time in class and also studying than you would in a 1 credit course. The formula states how we would calculate that. Mu, let's recall what mu stands for. Mu is the mean or the average, and it's the average of all the individual x's or your discrete random variables, which is going to be equal to the sum of each random variable times the probability it will occur, or the weight of each of those values. The mean of a discrete random variable can be thought of as the mean outcome of the probability experiment if we repeated the experiment many times. So if we suppose an experiment is repeated n independent times and the value of the random variable capital X is recorded, as the number of repetitions of the experiment increase, the value of the n trials will approach mu, which is the mean of all of the x's, the mean of the random variable x. So if x1 is your first random variable x, after the first experiment, then the average of all of your x's is going to be all of the discrete variables added together divided by how many were in your sample. The difference between x bar and the mean, let's recall again what those, they both stand for mean, but this is the mean from a sample. This is the mean from a population. So if we take a smaller sample out of the population and find the average of that smaller group, the difference between these is going to get closer and closer to 0 the larger the sample becomes. Again, that's using the law of large numbers. Because the mean of the random sample represents what we would expect to happen in the long run, it's also called the expected value. The interpretation is the same. So if I ask for mean, you could also say what would be the expected value in the long run. In order to calculate the standard deviation of a discrete random variable, you will use one of the following formulas. Here is standard deviation of a random variable x, and you can use either of these two formulas. They're both computational. Let's do an example using these formulas below. In the Sullivan Statistics Survey, 1,000 individuals were asked to disclose the number of televisions in their household. In the following probability distribution, the random variable x represents the number of televisions in the household. So I surveyed 1,000 people, and I asked, do you have a TV and how many do you have in your house? There were 0 households out of 1,000 that said they had 0 TVs. There was 161 households out of 1,000 that said they have 1 TV, and so on. The first question it asks us is to verify that this is a discrete probability distribution. In order to be a discrete probability distribution, we have to follow 2 rules. The first rule says that all individual probabilities have to be a number between 0 and 1, and that is indeed true. The smallest probability is 0 and the largest is only 0.26. So all the probabilities certainly do fit that characteristic. Also, we need to know that the sum of all of the individual probabilities must add up to 1. And if I added up everything in this column, you're going to see it adds up to 1. So that is also true. These are the 2 characteristics you must prove to be able to determine it in fact is a discrete probability distribution. We also know it's a discrete probability distribution because these values here are a discrete variable. They are countable values, not continuous, since you can't have 8.5 TVs. So let's go ahead and draw the probability histogram down below. So to draw a probability histogram, we need to draw our x and our y axis. The x-axis is going to be the number of TVs down here. The y-axis will be the probability of a household having that number of TVs. And you can see from the chart up here, we must range our x-axis anywhere from 0 all the way up to 9. Then we go through and we put in our rectangles for the heights of each of the individual probabilities. You can see that the largest probability that I'm going to need to construct my vertical axis for, I need to make sure that this is going to be my largest bar, which is 0.261 height in probability. So in my graph down here, I might want to make this up to a probability of 0.3. There's no sense making it go all the way up to 1 since none of my bars are going to reach that height. So now what I'm going to do is I'll draw the first bar for you. You'll see in my table how many of these groups have 0 TVs, and the answer is 0 probability. So there actually is no bar right there. How many households have 1 TV? Well, the answer is 161 out of 1,000, which is a 16% chance out of my grouping of 1,000 that they might have exactly 1 TV. So I'm going to draw a bar that is going to be 16% tall on my graph. What percent has 2 TVs? And you can see the answer is 26%. So I'm going to draw that bar 26% high. and so on. So at this point, I'd like you to finish the rest of this histogram by pausing the video now. Hopefully your graph looks something like mine. You can see this definitely has a trend where the most of the households have 1, 2, 3, 4 TVs. This is where the bulk of the data lies. Certainly there are some people that have 5, 6, 7, 8, 9 TVs. These might be considered outliers out here to the right. And this definitely does seem to have a skewness to it of a skewed right graph. So let's take this information a little bit deeper. We also know what we want to find is the average of all the TVs. Now, what would be incorrect if I pull this back over here? The original data, the wrong thing to do would be just to add all of these numbers together and divide by 10 since there's 10 options. And that would be wrong because we know that this column right here needs to be weighted a lot more heavily than, let's say, this column down here because it's not as probable or likely of occurring. So we need to weight 2 TVs a lot more heavily than we do 9 TVs, since there were 261 families that all have 2 TVs. So we're going to use a weighted average formula, or the formula that was given to us on the previous page, which was here it is, the mean of a discrete random variable back from the second page. So we're going to use that formula to determine what the average number of TVs are in this grouping. I also wrote the formula over here. So what we're going to do is we're going to calculate the average number of TVs. It's not going to be in the middle because we have a higher likelihood of belonging to one of these categories than we do here. So I already know it's not going to be in the middle. It's going to be somewhere more towards the beginning of my list rather than towards the end. So what we're going to do in order to find the mean of my random variable x, we're first going to take all of the individual random variables and multiply them by their probability. So we're going to take 0, which is our x. We're going to multiply it by the probability it will occur, and you're going to get 0. Then you take, 1 TV, which is my x, and what is the probability that they will have 1 TV? 16%. So when I multiply those together, I get 0.161. So if we continue on this method, the number of households that have 2 TVs in their household is 26%, and when I multiply those together, I get 0.522. And you're going to continue on down this method here, and when you get to the bottom, what you're going to do is you're going to add all of those together. And this number down here is going to be the sum of all the individual discrete random variable x's times each of their individual probabilities. And when you add all of those numbers together, you actually get the same thing, which is what our mean is. So I'm going to let you finish the table, and you'll be able to then determine what is the average number of TVs per household. So pause the video now. Okay, so hopefully your table looks similar to mine, and when I add up all of those values, I get a total sum of 3.21. So what I'm asking you to find is determine and interpret the mean random variable x. So the average number of TVs per household in the United States is 3.21. The United States has, on average, 3.21 TVs per household. Which again makes sense, because remember, I told you at the beginning the average was not going to be in the middle. Because of the heavy weights down here at this end, that mean was going to be pulled towards the heavier weights. Now let's determine the standard deviation. The standard deviation formula was given to you on the previous page, but I have also included it here. What we need to find is x squared. So you're going to take this value and we're going to square it. Then we're going to multiply that by each individual probability. which is here, and that's what I'm doing in this third column right here. So we're going to take x squared, which is 0 squared, multiplied by the probability in this column. Clearly we get 0. How about the next one? 1 squared, which is x squared, times its individual probability gives us this value here. Let's try it again together. So for the next value, we'll have 2 squared times the individual probability of 0.261, and that's going to give us a value of 1.044. Once we have all of those values here, and you add those up, that's going to give us the sum of all of the x squareds times each of the individual probabilities, which is going to be this portion in here. Just this portion in here. Once we have that number, then we find the average of the x's, which we found up here. This number is found from the previous example. And we subtract what we found down at the bottom minus what we found up at the top, and then we take the square root of that answer. So go ahead and fill in the rest of this table, and then we can finish to find the standard deviation together. Alright, so when I went ahead and did all of these calculations, and I added this whole right-hand side column all up together, I got 13.32 when I added those numbers together. Then what I'm going to do is I'm going to subtract the average or the mean from what I found up here, which was 3.21, and I make sure I square it. Then I take the square root of that whole answer. When I put all that into my calculator, I find that the standard deviation of the discrete random variable x is going to be 1.74 TVs. So what is the probability that a randomly selected household has 3 or fewer TVs? So we want to find the probability if I randomly select one TV out of all these 1,000 TVs that are in this list, and I randomly go in here and select one, or one randomly selected household. What is the probability that 3 or fewer televisions will be picked? So I want to find the probability that x will be less than or equal to 3, because it says 3 or fewer, so 3 would be included. So what we're going to do is we're going to add up all of the probabilities in the table that are 3 or less. So I'm going to add up all of the probabilities that are 3 or less. So we're going to add 0 plus 0.161 plus 0.261 plus 0.176, which is the probability of 0 TVs plus the probability of 1 TV plus the probability of 2 TVs plus the probability of 3 TVs. And when I add all of those values together, I get 0.598, which you could write as 59.8%. What is the probability that a randomly selected household has no televisions? So just 0, not greater than or equal to, just equals 0. And the answer is 0, because if you see right up here, there's a 0 probability that that will occur. But it says, would you consider this an impossible event? We designated back in Chapter 5 that if something has a 0% chance of occurring, it's impossible. So would you say it is impossible that a household in the United States has 0 TVs? Well, even though this probability is 0 for this particular sample, it does not mean it is impossible for the total population. Let's now also find these answers in Statcrunch. Okay, so if we were to do this in Statcrunch, the first thing I would do is I would put all of the data into my Statcrunch, the number of TVs and the probability of each occurring. You could either put this column in as probabilities like I did here, I see I have one wrong actually. Or you could put them as frequencies. That would have also have worked. But in other words, you just need to have the weights. Then what we're going to do is we're going to go to Stat, Calculator, and we're going to do Custom. Down here, the Custom, we're going to do a custom calculator because it's going to calculate the average based on different weights. So you have to customize the average calculator. So my values are in the X column, which is what I named it up here. My probabilities are going to be in the weights column, which is here. And when I compute this, you're going to get a histogram, which is going to look very similar to the histogram that we already created in our lecture notes. You can see that definitely is a skewed right graph. And the reason there are two different colors is because where half of the graph would be. So anything that is red is going to be left of the average. Anything that is black is going to be right of the average. So it looks like my average is going to be somewhere in here in between 3 and 4, which we already knew was the answer because we calculated it to be 3.21. What we could also do with this calculator is answer parts E and F again. So for example, for part E, it asks us, what is the probability that a randomly selected household has 3 or fewer televisions? We could add up the probability of 0, 1, 2, and 3 and add them together, or use the calculator down here. You'll notice that it automatically calculates the mean and the standard deviation. I can't change these numbers. It's already calculated, and those numbers should match exactly what we found up in parts C and D. So the calculator in Statcrunch is much, much faster at determining mean and standard deviation than it is by using the formulas like we did by hand. So to answer part E, we want to find the probability that a discrete random variable has less than or equal to 3 televisions. So I can change these values. I can say less than or equal to, and I can change it to 3 or some other value. When I change it to 3 and I compute that value, I get a probability of 0.598, which matches, again, what we have in our notes. If I change this value to 4, for example, and compute, I get a larger probability because you're now including this number in your probability. So the higher I include that number, the more they are going to be starting to be included. So now we're going to include that extra number, which means these red bars are being included in your probability. I could even do equals. So what's the probability that I will pick a household that has exactly 0 televisions? And you see that the probability is 0 because it doesn't have a bar. If I wanted to find the probability of something being in between two numbers, I could even do that by clicking on this other tab over here. So if I want to find the probability that I will randomly pick a household that's between 2 and, let's say, 4 televisions, which means it's going to be bars 2, 3, and 4 included. And you can see that here by the 3 red bars, bars 2, 3, and 4 included, the probability will be 62%.